So this is going to be a lightning talk. Let's see how fast I can do it. I want to share an idea with you that stems from this motivation. I think to avoid avoiding success at all costs, we need to provide our users with better tools to analyze and control the space behavior of Haskell programs. And I've been told by commercial users that this is one of the main problems. So here's an idea. Basically, first here's a problem. Sharing usually is good, but it can cause bad space behavior. So this is the canonical, the smallest example in a way. We allocate a large list. So this one looks like first, we have a tuple with thunks. They refer to this one thunk within the list. The first will be black hole, the thunk evaluate the list, it will become large. The memory is full of this list, we have the result, but maybe we didn't have enough memory to get this far. So what people currently do sometimes is they transform their code to avoid this. So they make the first, the list, not a list, but a function that returns the list, and they don't care about the argument, so they use the unit. And this might work well, so both these thunks refer to the function, the first one gets evaluated, calls the function creates a new thunk representing the list, and while we traverse the list, the garbage collector can clean up behind of us. So at the end, we got the result, the long list has never been fully in memory, and now the second thunk can start working. Unfortunately, sometimes the compiler might optimize things away. For example, it might float out the list, and suddenly you get the behavior you want to avoid. So here's my idea. I'm not saying it's perfect, but it's a good idea first. We introduce a command that the user can use to say, okay, I want this not to be shared. So we duplicate the thunk in a way. So what happens, basically, it looks very much similar. When the first thunk is valid, it creates a copy of the thunk on the heap. And now I evaluate this copy. It might get updated by some reference anywhere else. So the garbage collector will again clean up behind of us. And we got no sharing, and we got the always one space behavior. Note that in this case, it's the consumer of a thunk, not the generator that decides that we want to avoid sharing, which may or may not be what we want. And especially that it didn't have to do any code restructuring, and as in changing the types or changing the generator code at all. So this might even work if the thunk that you're working on comes from code that's not under your control, say some EDSL framework or something. Now, if you know how the runtime works, you might think, okay, this looks fine, until the list that I'm talking about has already been evaluated, say, a few cells. Then I would just copy the first const cell, and I still share the rest of the list. So for that, there's a stronger version of it. It's deepDup. What it does, it not only duplicates the thunk team, but it also replaces references of the thunk to other things by deepDup closures that will, once this thunk, the copied one, uses it, again copy the stuff. So we essentially get a complete copy of the heap, but we don't copy the heap, we just do it lazily. So there's a guarantee that if I evaluate something, C's constructors, I's, I don't know. So if I evaluate something that is wrapped in deepDup, and the result is, say, integer, then at the end of the evaluation, I have not touched any of the remaining of the original heap at all, which is an interesting guarantee that we can actually give for this. There's a proof in the paper about this against launchberry and semantics, so it's not just byte hackery. And you can read more about it in a paper that I didn't get to present here in full length, so that's the lightning talk. The implementation is not in Hackage because it's not that stable yet, but you can get that code there, and it works without modifying your GSC. So you can just play around with it, and that's what I want to invite you to. And since I'm very fast, I get to choose two other ideas that I have. So this is one idea, the main one. Later I looked at a different perspective and thought, okay, what if we make the generator of a value decide whether it's going to be shared or not. So for this, I introduced a function that looks like the identity. Now for this, I have to change THC. But if this function is the outermost thing in the body of a thunk, then THC will not make the thunk updatable. Basically, it will skip generating the update frame, you know what it is. It doesn't do any black holding, so it saves time, it's faster. And you don't get any sharing. So I think things like list of numbers from 1 to something very large will rarely be useful to be shared, and rather more useful to be recalculated. And for that, you might want to use this primitive. If you want to play around with this, ask me for my HIW branch, or find it on GitHub. And since I still have time, I also want to show you something that a student of mine, a bachelor student of mine did. Basically, now about the analyzing thing. Down here is a very famous code. It's calculating the prime numbers in 2 lines. And if you want to know how it works, you can now use thus, VS, which is running up there, to look at it. It's very similar to vacuum, if you know vacuum, but it also shows what thunks are doing. So we see that prime is a thunk, and if I evaluate it by clicking on it, so this is like an interactive seek, I see the heap structure of what comes out. So there's an interaction because it was a cuff, and then the const cell referring to a thunk, referring to 2, and then the thunk referring to 2 and 1. And now we can actually evaluate thunks that are hidden behind thunks. You can't do this from Haskell, and you can't do it from the GHC debugger, I think. So we can see, okay, this seems to be the list of all potential numbers. Now this thunk seems to throw out everything that's a multiple of 2. So the 6 disappeared, and okay, let's get some more numbers. So now the 8 will disappear, so this will be 9. And here we will throw out everything that's a multiple of 3, and this way you get all the primes. So this is a nice tool you can play around with, or you can use in education. It's on Hackage. We just yesterday blogged about it in Haskell, so there's a link on it. And that was my lightning talk. Thank you.
Go back to no update. No update. User interface on microphone failed. What happens if I say let x equals ID of no update blah?
Well, hopefully the compiler will get the idea away, and you still get the thunk. It's difficult because it doesn't matter what you write here. What matters is what happens at the core after all transformations. So it's the core to STD phase that does the no update. So I'm not saying it's user friendly. You might want to use commit to look at the core and see what happens with the no update at the very end. Yeah, it's a rough idea. But yeah, that's of course a problem with both of these approaches.
The no updating, how does that propagate? Because the thing is creating thunk on the outside, but the moment you ask for the moment you ask for the first element, the moment you evaluate the thunk, you get back a new thunk in the tail. And how do you propagate that no update to the tail? Because I assume, I think the battery's down. Because I assume you also don't want to update the tail thunk.
Right. Okay, so this is basically a simplified display. So let's have a look at some example code. So find where I have it. Yeah. So testing. So this is how I would intend it to be used. Basically, if you write your enum function for ints, then you know that every tail you want to not be updated. So you would put it inside the enumeration function. That was basically the idea. Yeah.
You can save the rest of the questions for the break.